Okay, there we go. Okay, so new topic for today, starting section 2.6. So we're going to define something called directional derivatives. I'm going to lead into this in a kind of an unusual way. I'm not going to derive formulas. I'm going to make a kind of a hand-waving, impassioned speech to try to persuade you that this seems plausible. Right? I could derive these and, do the calculations, etc. It's just more time consuming, and ultimately, I think the intuition's more valuable to you anyway. Alright, so here's what we're going to start with then. We're actually going to start with kind of a summary, revisiting of partial derivatives. And here are some things that we know about partial derivatives. On the one hand, partial derivatives are the slope of the graph of the function. Now, specifically as you move in the direction of that vector. Partial derivative also can be thought of as it's a multiplicative factor, right? Remember, this is one of my big points of view that I push on how to think about derivatives. Derivatives are factors that you multiply by input changes to get output changes in some sense. I mean, more broadly speaking, they're relationships between input changes and output changes. But the partial derivative in particular is a multiplicative factor. Okay. Let's see here. Now, we haven't exactly talked about this before, but here's a rewrite of the definition of a partial derivative, and I know this doesn't look familiar, so let me walk you through it. Remember, what we actually do when we take a partial derivative, the way we've defined it in the past, is hold all the other variables constant, and then just take a regular single variable derivative with respect to the one actual remaining variable. Well, I claim that that's what this formula does. Right? This says, look, I've got some point A. Fine, I'm going to stick to that point A. That point A is most of the variables. All the variables except for one are going to stay constant. Notice when I write this down, that remains the case, right? This vector here, other than in the ith coordinate, this doesn't change it just doesn't do anything to A at all. Right? Adding this doesn't change, all but the ith coordinates stay constant. And then I am going to take the derivative with respect to t, but t is how I changed that ith coordinate. So this is a plain old regular single variable derivative with respect to as you change that one coordinate. So anyway, this is just an alternative point of view on how to define partial derivative. And then, of course, we also have this formula for partial derivative, which is, again, maybe not something that we thought of particularly in the past, but if you recall that the gradient vector, after all, is made up of all the partial derivatives. And dot product with the standard basis vector, after all, just picks out the corresponding coordinate, then it's going to give you that corresponding partial derivative. Okay. By the way, you can also set it up so that you think of this as a special case of the chain rule for your consideration. Something to play with if you're entertained. Okay, so here's what we've got. Now this is a bunch of facts about partial derivatives, much of which is review, but notice the way I've phrased this. Everything that I've got written down here, nothing says anything about coordinates. Right? So I didn't say hold all the other coordinates constant. I said here we've got a position, right? And we're going to move by way of a vector, right? Which you could think of in terms of coordinates, but you don't have to. Right? So what we've got here then is this is a great big description of partial derivatives entirely independent of coordinates. And now, one of my other motivations actually to present, to take this kind of approach to where we're going to be going in a few minutes is that it's a good opportunity for me to remind y'all that, coordinates are a way to think about things, but they're not required, and there's really nothing particularly absolute about them. I mean, y'all remember in linear algebra, there's this change of basis thing, right? Any basis that you pick for a vector space, kind of arbitrary. And you can do a change of basis and just reconceive of everything in the question with respect to a different basis, and there's nothing wrong with that at all. Right? So when you're doing multivariable calculus, yeah, sure, variables. If we need to get something, on paper, we've got to get our hands on the problem in some way, and variables are good for that. Coordinates are good for that. It's nice and convenient. But you don't have to. It's not really intrinsic to the functions that you're looking at or the points that you're plugging in, that you think of them in terms of coordinates. So a coordinate-free point of view on something is arguably more fundamental. Right? And this is a coordinate-free point of view on partial derivatives. Stated entirely, again, as you'll notice, in terms of vectors. Right? The only things indicating which direction we're going here is this vector. Okay, so that noted. If there's nothing special about coordinates, and if what we're saying here, if this slope in this factor and this expression and that expression are all the same thing, when we're talking about in the direction of that unit vector, well, there's nothing special about that unit vector. Why wouldn't all of these things also equal to each other when you're talking about any other unit vector? Why not? Right? There's no reason. There's nothing special about this vector, and so this ought to work. This sort of coincidence of properties, this simultaneousness of properties, should work in the direction of any unit vector. That's the big idea of a directional derivative. Directional derivative says, okay, I want to reproduce all the stuff that we got here. I want to rip off the idea of partial derivatives, and I want to sort of, get all the goodies, everything that we used to know about partial derivatives to come along for free, and just in the direction of any arbitrary unit vector. In other words, in any other direction. So that's the idea, and here's the statement. Now again, it does have to be a unit vector v. So you'll notice in particular that's a unit vector. That's a unit vector, etc. Unit vector, etc., etc. But that said, this thing, just like in the previous case, ought to equal to that thing. Same ideas, different direction, whatever. And those things ought to be the slope of the graph of the function as you move in a certain direction. They ought to be the multiplicative factor that you multiply by blah, blah to get blah, blah. Right? So these things ought to be equal no matter which direction you're going, no matter what unit vector you pick. And when you're not going in the direction of an axis, in the direction of a standard basis vector, we can't call it a partial derivative, but this is still an interesting thing. It's a connection between a lot of different ideas, so we give it a different name. We call it a directional derivative, and we use this notation right here. Note that this notation indicates where I'm computing this thing. Know what point A am I sitting at. It also indicates in the notation in what direction, in what unit vector direction am I going. So I'm just going to assert, with intuition as my justification, that these things should all be equal, and this is a perfectly interesting concept, and we're going to give it a name and a notation. So there we go. Directional derivative. Now, a few things to say about it. Conveniently, by the way, I have a pretty handy formula here for how to compute this thing called the directional derivative. A dot product with the gradient. Right? By the way, this is also a pretty believable way to prove the results that we're claiming, is to notice that this dot product with the gradient pretty suggestive of the chain rule. Right? In fact, again, if you set it up a certain way, you can think of this as just the execution of the chain rule according to a certain setup. So I hope that makes this seem more plausible. But this thing, the directional derivative, which I can compute with that formula, which I can define with this formula, is the slope of the graph as you move in that direction, and it's the multiplicative factor as you move in that direction. All right. So So just to get a picture, so we can so see what's going on here. Previously, when we have been at let's say a point like this point here, we've talked about, all right, well, if you go in this direction, how does the function change? Or if you go in that direction, how does the function change? And now I'm just saying, okay, well, yeah, sure, right, but why not any other direction, like that direction or that direction or that direction? Coordinates are a highly optional point of view. I don't want to say they're an illusion, right? But I mean, they're not absolutes. They're just a convenience. And so that we expect that this ought to be true. Okay. All right. So yeah. So if you're going, for example, in that direction, then we could imagine a vertical cross section plane there. The cross section of the surface would be a curve. There's that cross section of our surface, and I can talk about the tangent line in that direction, and the slope of that tangent line gives us what we call the slope of the graph. So it's computing, morally the same thing that partial derivatives do. How we doing? Is everybody on board? Willing to buy it? Rigor aside? Okay. Now, as a notational thing, let's look at what we've got here in item number 2. This thing called the directional derivative. Again, it's a multiplicative factor. It's what you multiply by input change, measured either as a distance, right, or as a speed as you're moving in that given direction. Take your pick. It's what you multiply by input change to get output change. Again, understood accordingly. So if this directional derivative that I have in green here, this thing here, if that's the thing you multiply by blue to get orange, and then you look at how this equation here shows up, doesn't that make it seem like you should interpret directional derivative as being df/ds? Right? It just notationally, if nothing else, it seems like it'd be a reasonable way to think about that. So this leads to another nice interpretation of the directional derivative. The directional derivative is the rate of change of the function as you move in a certain direction with respect to distance traveled. S being distance, right? So it's not how fast is the function changing per unit time, it's how fast is the function changing per unit distance. So here's just an example for relatability purposes. As y'all know, I like to think of graphs very often as being hills, right? So imagine that this is a hillside, and you've got a hiking trail or a road or whatever that you're moving along there. As you're moving along that road, you could reasonably ask, sure, how fast is my altitude changing per unit time? Right? If you're interested in the air pressure in your ears and you're getting that earache thing, and should I do the jaw thing to get rid of that pressure, that's about how fast altitude is changing per unit time. Very naturally interesting thing. But also very interesting, different reasons. How steep is the road? That's rate of change per unit distance. Altitude change per unit distance. And that's what directional derivative computes in this interpretation. Directional derivative, rate of change of the function with respect to distance. And the height is not the only situation that this would be interesting. Notice that this concept, rate of change of a function with respect to distance, it makes sense in any context. Like maybe I'm keeping track of temperature in this room, and it's probably warmer by the windows where the sun's coming in and colder in that dark corner over there where there's no light. So temperature varies. I could reasonably ask, at this point, right here, pick some particular point, if I were to start moving that direction, let's say, if I start moving in a certain direction, for every inch that I move in that direction, how much does temperature change? Right? Very reasonable thing to want to ask. I haven't decided how fast I'm going to move in that direction, so don't ask me about time rate of change. I'm not even moving yet. I'm just contemplating a move in that direction, and as I contemplate a move in that direction, how much would the temperature change per unit, per inch that I move or what have you. Right? So, also what directional derivative gives you. All right, let's see some examples. Okay, so we got a function. Question asked me for the slope of the graph at a certain point in a certain direction. Slope of the graph, of course, is one of our primary interpretations of directional derivative. So back up to here. Directional derivative, right, denoted like so. Slope of the graph. So I want to compute a slope of the graph. I want to compute a directional derivative. And, of course, I have this handy-dandy formula for directional derivatives. So all I have to do is compute the gradient, find the unit vector in the relevant direction, and now this is an easy to lose track of little detail, but all this stuff we have back here, this coincidence of all of these properties of the formulas and the interpretations requires that this be a unit vector. Please do be careful with that. That is an important requirement. Okay, so I was asked in this question to move in a certain direction, but the direction was described in kind of a sloppy way, right? Well, you know that direction that this vector points, right? I mean, 3-4 is a vector. Vectors do have a direction. That's the direction I want to be moving, but that's not a unit vector, and so I can't let that be. I cannot say directional derivative in the direction, with that as my v vector. Doesn't satisfy the rule. So, okay, fine, I've got to find the unit vector, and the unit vector, no problem. You take the vector in question, and the unit vector is, it is the given vector divided by the magnitude of that given vector. And so here we have an actual unit vector. That's what I dot with the gradient. Computing the gradient, of course, now let me gloss through this real quick because this is old news. The way we take a gradient of a function... let me try that again. The way we take a gradient of a function is to take the various partials, and those partials turn into that. A little bit of algebra y'all can do. Of course, we have to evaluate at the given point 3, 1, which turns this function, this gradient vector into that, and it's all over but the arithmetic. How we doing? Everybody okay? Real quick point of language. You do have to be very careful how you interpret the question. The question says that we are, let me just come down to here. There's more space. Says we are at the point 3, 1. Here's the point 3, 1. And then it says I am moving in the direction of the vector 3, 4. 3, 4 would be about like that, right? And so I find this corresponding unit vector here, which is unit vector in that same direction. So here's a picture of what we did, and at least as far as the domain's concerned. Be sure to interpret direction of the vector, thinking of this as a vector. It says the vector v. Vectors do have a direction. This is a reference to the direction of that vector. I mean, that direction. Right? Don't make the mistake, and this is the following is wrong and tempting, but very much not what's indicated here, of thinking, I'm going to interpret 3, 4 as a point. 3, 4 as a point would be like here. And interpret this as saying toward that point. Well, notice, toward that point is a totally different direction. And it's really not what this question's asking about, right? So I know that they kind of sloppily, casually sound the same. In the direction of the vector sounds like toward a location, but it's not. Right? Is everybody okay with that? Does everybody see the distinction that I'm drawing and why this needs to be interpreted the right way? Okay. Cool. Yeah, there's a lot of detail doubles, I'm sorry to say, in math, but certainly in this class. So heads up. All right. Next example. Now again, here's one where we're not going to be looking at the graph. This is just temperature given as a function of position. And I've got a function. I'm at a certain point, and I'm moving in a certain direction. Again, heads up, notice I don't mean toward a point. I mean in the direction indicated by this vector. And reasonable question. Whoa. How fast is the temperature changing as I move in that direction? Right? And again, I don't know how fast it's moving with respect to time. I haven't even decided how fast. I don't have a velocity vector. Who knows how fast I'm moving? So I can't begin to even ask the question of what's the rate of change of temperature with respect to time. But I can talk about rate of change with respect to distance. After all, that is the directional derivative. Again, refer you to the previous page. This is one of our interpretations of the directional derivative. It is df ds. Rate of change with respect to distance. So, that's, we've identified what we need to compute. We have a handy formula for computing it. Again, we just need to compute a gradient. Plug in the values. Don't forget to unitize the vector. The algebra from here is really pretty much the same. So again, you can compute. Missed again. Got to get more careful with my circling. There's a gradient. We plug in that point, which gives us that, which is the gradient that we dot with. The vector in question, again, I have to unitize that. The unit vector is going to be the vector in question divided by its own magnitude, just like in the previous question, and arithmetic and victory. What do you think? Everybody happy? Cool. All right. Now, I'm sorry to report that there is there are different usages of this term directional derivative, and this is under-discussed, in my opinion. Everyone seems to think that their point of view on directional derivative is of course, it's perfectly obvious. Anything else is ridiculous. I guess it's not the only such case in the world. But anyway, heads up, while our book, and therefore our course, does have the very important restriction that this has got to be, and this is non-negotiable in Math 219, a unit vector. If you're going to use the term directional derivative, then it's got to be that vector is a unit vector. In other contexts, they remove that requirement. And with good reason. The good reason is that, let's suppose I were to scratch out this requirement here. Let me just scratch out where it says unit. Suppose I'm moving as described by any other vector, unit or otherwise. How fast the function is moving as I go in that direction with that velocity, still interesting. This is a very natural construction to want to talk about. If I interpret v as a velocity, this expression here that I have circled tells you how fast the function's changing when you're at the point A, moving with that velocity v. Still interesting. By the way, just so you know, it's still computed by this same formula. Again, even without the unit vector requirement. So why are we worried about all this? Well, the thing is, if you remove that unit requirement, then this thing is no longer the slope. It's also no longer a multiplicative factor. So all of this interpretation down here goes away. Right? But nevertheless, it's still an interesting thing. It's still a natural thing. And this, as described here, is outside of Math 219, and in a lot of circumstances outside of Math 219, still referred to as a directional derivative. So heads up. By the way, this is not my fault. I didn't do it, right? But I just want to make sure that y'all are aware. When you're outside of Math 219, if you hear someone say directional derivative, you should think, what do they mean by that? Do they mean unit vector, or are they off talking about non-unit vectors? Because you need to know whether or not you can make these interpretations down here. Right? So I'm just going to say again, heads up, outside of Math 219, be on the lookout for that possibility. Okay. So again, though, just to be clear, in Math 219, unit vector required in order to use the word directional derivative. And as such, then all of the goodies come along as a result. Okay, so sorry about that. Again, not my fault. So just to be aware. Okay, so here's a question that is kind of about directional derivatives. Certainly a question that directional derivatives is going to help us answer. And so here's the scenario. Suppose I have some multivariable function. I like to think of this as being temperature, just because I don't want to be stuck with a graph interpretation. I don't want my understanding of this question to be dependent on a point of view, right? So I like to think of temperature. To me, it's the most viscerally relatable day-to-day function of position that I can kind of think in terms of. So anyway, I'm thinking in terms of temperature. So that said, let's suppose this is me right there. I'm at that point A, and I'm contemplating what direction I should go. Maybe I should go that way, maybe this way. I don't know. That direction looks nice. I've got a bunch of different directions I could start walking. Which of these directions makes the temperature increase the fastest? Very natural question to entertain, right? I'm cold. I'm going to warm up. Which way do I walk? I can walk any direction. Which way? Is everybody on board? Now, I emphasize we are restricting the question to unit vectors because I want to exclusively entertain the question about which direction should I go. To the next question of, with what velocity, with what speed should I go in that direction? Yeah, run as fast as you can. Of course, that's a given, right? So, of course, I'm going to run as fast as I can, or as fast as the social circumstances allow, right? I'm a fast walk, maybe, right? But the speed is not the question at hand is not about speed; it's about direction, and so we're going to make that happen by requiring unit vector. And I want to make the temperature increase as fast as possible. So I want the, how fast the function changes, df/ds, to be as great as possible. So I want to maximize the directional derivative. Everybody see how we're going to therefore answer the question? We're going to have to figure out how to maximize that directional derivative. Okay. All right, now before we get to the answer, let's talk about language a little bit. So the eventual answer, whatever the direction is, let's say it's that way. That direction can be described in two different ways. It's the direction that maximizes the directional derivative. Okay, but what does that mean? What is the directional derivative? The directional derivative is telling you how fast the function is increasing. So direction of fastest increase is a pretty reasonable thing to call this. Right? Whatever direction I go to make the function increase as fast as possible, direction of fastest increase. Now, if you're thinking about graphs, which is a big if, right? Graphs are awkward to draw when the dimensions get high enough. But if you are thinking about graphs, then in that setting, a directional derivative, of course, is it's the slope of the graph as you're moving in that direction. And so if you want to maximize your slope, namely how steep the hill is, how steep the graph is, steepest, right? Maximizing steepness, we would say steepest. So this is the direction of what they call steepest ascent. This is the direction which, if you go in that direction, climbing the hill is as steep as possible. So, FYI, both of these terms are they're both out there. I do think this term here is a little bit more classical and a little bit more common use. But frankly, I don't like it as well. Because again, in order to make sense out of this term, in order to even talk about steepness, you have to be thinking about things in terms of graphs, which we might not be. We might not be able to. Right? So having a terminology that is motivated by a geometric perspective we might not even be able to have, I don't think that's a good... I'm opposed. I think it's a bad choice. I think it's just as reasonable and always applicable to say direction of fastest increase. Now, when I took multivariable calculus, my teacher used this term here. And so I have to kind of force myself sometimes to not say direction of steepest descent because, I'm now sort of philosophically opposed to it. And I force myself to say direction of fastest increase. So you're going to hear me say steepest descent here and there. And it's not the worst thing in the world because, again, it's out there. It's a common term. You're going to hear other people say it. But I encourage you to think in terms of direction of fastest increase. Okay, so we've spent a lot of time here talking about the question and the context and how to think about it and terminology, etc. But is everybody on board and ready to now finally answer this question? Okay, here we go. How are we going to answer this question? We want to maximize the directional derivative. Okay. Well, here's the directional derivative. It's gradient.v. That's the thing we want to maximize. Let's see here. Dot products. Here's the formula for dot products. Very generic, right? Dot products can always compute it in those terms. Fine. So this is what I want to maximize. Oh, don't forget, this is a unit vector here. And that means that this magnitude here is 1. And so I can throw that factor out. The thing that we actually want to maximize then is this expression here. And if you think about it, if I've got a gradient vector at this point that's pointing that way, and I'm entertaining various different possible directions that I could go, as I scan around and look in different directions, does the gradient vector move? No, not at all. The gradient vector stays right where it is. Gradient vector only depends on where I am, not what direction I'm looking. So the gradient vector is fixed, and therefore its magnitude is constant. Right? That magnitude of the gradient is independent of all of these different contemplations of which direction to go. So, where we land then is that if I want to make this directional derivative as big as possible, I just need to make cosine theta as big as possible. That's easy. Cosine theta is maximized when theta is equal to 0. What is this theta that we're talking about? Well, see this theta here. That's this theta from this formula. It's the angle between the two vectors that I'm dotting. So I want that angle, apparently, if I want cosine to be as big as possible, I want that angle to be 0. And that makes cosine 1, and that makes this directional derivative as big as possible. So I just need for this angle to be 0. And if you think about it, that means that this vector here, its angle off of the gradient needs to be 0. That means that that green direction vector needs to be the unit vector pointing the same direction the gradient is. So it's that. Everybody okay? All right. So it's a nice little argument. Natural next question. How steep is it in that direction? How fast is the function changing as I move in that direction? Right? This is the direction that makes the function change as fast as possible. How fast is it? Right? Like a joke. So easy computation as well. If you want to know what is the rate of change of the function in that direction? The direction being this that we've already computed? Right, well, then you just proceed with the with the computation as this has already started. There's our formula for directional derivatives. And then I can take advantage of the fact that this dot product is magnitude squared. And then I get magnitude squared divided by magnitude, which is magnitude. And so there's that answer to the question. So the direction of fastest increase is that expression, and how fast is the function changing in that ideal direction is that expression. How we doing? Is everybody on board? All right. Now, I like to phrase this in a different way. If you notice, the answer to the first question here, what's the direction of fastest increase? That's the direction of the gradient vector. The answer to the second question is that's the magnitude of the gradient vector. Direction and magnitude. The two geometric defining characteristics of a vector, direction and magnitude, are the answers to these two very natural questions. And so if we take the above analysis and kind of rephrase with that in mind, we have kind of a new interpretation of the gradient vector. The gradient vector, previously we've thought of it as it's a notational shorthand. I don't want to write out all the terms of the linear approximation. It was bulky, so we noticed it looks like a dot product. We made up a notation. We just called it the gradient. It was purely notational convenience. Now we have a geometric characterization of it. The direction is the direction of fastest increase. The magnitude is how steep is the mountainside, if you again, graph point of view. But what is that maximum rate of change? Purely geometric characterization of the gradient. So now we no longer have to think of and refer to the gradient as being a notational convenience. Now it's a natural thing. And we should probably primarily think of it in these terms going forward. Is everybody on board? Does everybody see what I'm talking about? All right. Okay. So here is a related question. Suppose you're hiking around and there's a hill that happens to be exactly in the shape of this graph, which is just a code for here's altitude as a function of longitude and latitude, right? Height as a function of location. So let's suppose I'm sitting at this point. The point sitting above 1, 3, and let me distinguish that from 1, 3, which you might say is sort of down here. And now that I've made that distinction, let me apologize for this awkwardness. We very often will conflate these two things. Because, think about how you describe locations on the surface of the earth, right? You describe them with longitude and latitude. Nobody says, here's my longitude, latitude, and altitude, because that's pretty much a given. I mean, I guess if you're hang gliding, then maybe you need to tell them your altitude also, right? But if it's understood you're on the surface of the earth, then longitude and latitude does it. And there's really no need to give any more information. So where am I? I'm here, of course. I am not, buried 50 feet under the surface of a hill, of course, right? And yet, very often, we won't be as careful as I was here. I say I'm at the point sitting above, right? Very often I'll say I'm at the point 1, 3. And you have to interpret reasonably from that he's not at the bottom of a well. He's on the hill, and 1, 3 are the x and y coordinates, and the z coordinate was he's on the hill. It's whatever the z is, whatever the value of the function is his z. Does that make sense? Okay, so apologies for that awkwardness, and it is what it is. Okay, so here I am, and again, my coordinates, my input, my x and y coordinates in question are 1, 3, and I want to know where I am. Which way is uphill, and how steep is it? Right? Very natural questions to ask. Again, if you're standing on the side of the hill, nice to know which way is uphill and nice to know how steep it is. Perfectly natural. So, well, again, the gradient is the answer to these questions. Which way is uphill? Oh, whatever direction the gradient points is uphill. How steep is it? Oh, well, whatever the magnitude of the gradient is how steep it is. And so we compute the gradient. Again, computing the gradient algebraically is just a matter of taking some partial derivatives. Of course, I'm interested in what's happening at the point where I'm actually at. Right? I'm at this point 1, 3. I'm sitting on the graph above the point 1. I'm at 1, 3, and you plug that in here, and so here's my actual gradient vector at the point in question. This is that vector. And so which direction does that vector point? Well, I'm going to call that direction southwest in the sense that, north would be typically, in the positive y direction. So if that's north, then this is southwest. And how steep is it? Well, whatever the magnitude is there, yeah.
So is the gradient 0 at the highest point?
Yes, that's right. The gradient vector is the 0 vector at the top. That's right. Yeah, and that's going to be relevant to when we get to optimization at the end of the course. That's going to be one of our big tricks for how to find that where's the top of the mountain, or where is my function maximized, is going to be exactly that trick. Yeah. Okay. Is everybody happy with this example? Yeah.
So a question. So how if we wanted to find the opposite, what's the
Oh, yeah. If you want to find which way is downhill and how steep it is as I roll down the mountain, it's just minus sign. Yeah, so the exact opposite direction. We're assuming here that all functions are differentiable, and so, minus sign does it. Yep.
It was bimodal and it has 2 peaks. Would it be if there was another peak that's like that somewhere else?
I understand. A great question. So very importantly, my assertion here is not that the gradient points toward the peak. Now, it does coincidentally happen to point toward the peak here, but that's because this is a highly symmetric mountain, right? It's a perfectly rotationally symmetric around whatever that axis is. But most mountains aren't, right? And most mountains, if the peak might be up that way, but the particular face that you're on happens to be that way where you are here. Right? And so this business about the gradient is only answering that local question of, myopically, I only see, 3 feet in any direction from where I am. Which way is uphill at this point? Which way do I go to make it as steep as possible? And the mountain kind of curves around. Maybe the mountain top is over there somewhere. Does that make sense? Yeah. That's a good question. Yeah.
So I wanted to ask, for example, if you're in a valley, right?
Yep.
And you wanted to get out the way, not the steepest, but the least steep path. So.
That's a question that doesn't actually have an answer, probably, because the answer would be do switchbacks, right? But do switchbacks no matter how gentle of a grade you do on your switchbacks, you could always have more switchbacks, and it would be even more and more gentle. So there's not a crisp answer to that question. Yeah. Okay, cool. So here's another neat thing about directional derivatives. It's going to help us understand the calculus of level sets, which we've only got a certain amount of calculus of level sets as of the moment. But here's a little bit more. So suppose I have a function, nice differentiable function of n variables, and suppose I'm looking at a level set where f is equal to whatever, some constant. Who cares? Okay, so here we go. I've got a level set S. And I'm going to make a couple of observations here. If I'm at this point on the level set, the value of the function is C, because I'm on the level set. If I were to move along the surface of that level set, value of the function's still C. I'm on a level set, so the value of the function's not changing as I move along the level set. So, function's not changing at all as I move along the level set. Here's another way to say that. As I move along this level set, that means I'm moving in the direction of a tangent vector to my surface. And so as I move in that direction, I'm moving along the level set. The function's not changing at all. It's remaining fixed, constant C. And so again, df ds. As I move in the direction I see now of any tangent vector, df ds is going to be 0. Is everybody buying it? The function's not changing. It's a level set. So of course the derivative is 0. But now let's remind ourselves, well, wait a second. If you're talking df ds being 0, now what that means is the directional derivative is 0, because that's how you compute df ds. And directional derivatives are computed with dot products. So in fact, then connect the dots, and no pun intended. And what we end up with is that the dot product is 0. This dot product here is 0 for every tangent vector. And that means that the gradient, by virtue of dot product with every other vector, every tangent vector being 0, the gradient is perpendicular to every tangent vector. And if we draw a picture of that, right, we've got all these different tangent vectors down here. That's just a handful of them. Of course, there's an entire plane of tangent vectors. You might say, in fact, that the tangent plane is the plane that is defined by all these tangent vectors, right? Well, if the gradient's perpendicular to all the tangent vectors, then the gradient must be perpendicular to the tangent plane. And therefore, the gradient is perpendicular to the surface itself. So, that's the really cool fact. This is a huge piece of what I like to loosely call the calculus of level sets. Gradients are always perpendicular, right? Perpendicular to level sets, and therefore they're tangent planes, and vice versa. Gradients are perpendicular to level sets. Cool fact. Everybody on board? Okay. All right. So I'm going to revisit now an old question that we already know the answer to for the purpose of giving a different approach to answering that question. Namely, how do I find the equation of a tangent plane? And we made an argument there about tangent planes and partial derivatives. And, well, I mean, if it's, graph of the linear approximation, we had a whole point of view there. So here, I'm going to take a different point of view. And that is, if I'm looking at some graph, right, this surface here is a graph of some function f, and I want to find the tangent plane. Fine. This tangent plane that I'm looking for, though, man, wouldn't it be nice to just be able to just instantly say, hey, I have a normal vector for that tangent. But wouldn't it be great to just have a normal vector instantly and not to have to make arguments about linear approximations and stuff like that? So, do I have any theorems about vectors that are perpendicular to graphs? Sadly, no. But I do have a theorem that says that every graph can be reconceived as a level set. Right? You can pull this little fast one right here, just kind of take the f and move it to the other side of the equation. Now I'm literally looking at a level set. You can see right there, set's equal to a constant. So I have a level set of now this new function G, right? And same surface, same question. I'm interested in the tangent plane to that surface. I want to find a normal vector, therefore, to that surface. Do I have a theorem about vectors being perpendicular to level sets? Why, yes, we do. Vector perpendicular to level set, bam, right here, gradient is our answer. The gradient of whatever function whose level set we're looking at. the gradient is perpendicular to that level set. So sweet. I just need to then take this function whose level set I'm looking at, right? And its gradient, which is easy to write down. There it is. Its gradient, it doesn't quite fit, does it? Its gradient is my normal vector. It's my tangent plane, and it's all over but the shouting at this point. Once you have the normal vector, you got to plug in the point in question. But there's your normal vector, and n dot x equals n dot x naught, right? And plug in and solve for z, and this z that you solve for, you get this very familiar old expression. Choices. You get this expression, which is exactly the graph of our linear approximation. So same exact answer we had before, just from the point of view of calculus of level sets. Y'all have a good day. See you later. See you Wednesday.